Yeah, well, in the future, I guess it'll get better. All right, so that took us quite a long time. But I want to talk about this fingerprinting stuff, which is what today's lecture is about. And fingerprinting, so what I'm talking about is, this, what I think of as the Shazam app, although Shazam is not the only one that does it now. But the idea is you've got a little chunk of music, a little excerpt of music, and you have a database which probably contains that piece of music, but you don't know which one it is, and so you want to match it. And then in the Shazam case, you're doing it with a mobile phone, and the music's being played over some speakers, and there's other background noise going on. And so you want to make it work despite the changes in channel, right? If you actually look at the filtering that the speaker and the phone mic apply, then it's pretty extreme. And then all this other additive distortion or noise. And you can use it. You can use it just for this kind of curiosity-driven thing. It seems like, why is this a big deal? But people actually really people find it very satisfying that they hear a piece of music and they either think they know what it is and they want to confirm it, or they wish they could remember what it was because they recognize it and they want to know what it is, or they're curious about it, and just being told straight off what it is very satisfying. So that's kind of surprising, but very real application. And there are these more pragmatic things like, artists are paid, get royalties depending on how often radio stations play their particular music. And so there are companies who exist to keep track of how often a radio station will play a piece of music. And obviously you can do that automatically if you can recognize it just from the radio sound. There's other technologies that have been used, but that's kind of the simplest. Now, the reason that fingerprinting is so interesting to me is that it's one of those cases, one of those rare cases, where the technology works much better than it seems like it should. So actually, the guys who started Shazam, when I was a research scientist in Berkeley in 2000, and they were two of them were business school students at Berkeley, and they took me out to lunch, and they said, "Oh, we got this great idea. We imagine this thing where you hold up your phone, it tells you what the music is." And I said, "Yeah, that would be really great, but there's no way you could do that." I was working in speech recognition at the time, and we were dealing with people speaking stuff, and even if there was almost indetectable background noise, the speech recognizer would just fall apart. And so for me, the idea that you could do it even with just the distortion of a speaker was like this. The statistics are going to change so much that it would never work. Fortunately, they went down the road and spoke to Avery Wang and Julia Smith at Stanford, who, in a couple of months put the system together. But as we'll see, the way they do it is very different from how speech recognizer works. And I would love to know the story of how they came up with this idea, because it's a very clever idea. So it works amazingly well. And any time that happens, my instincts are, okay, we should pay attention here because there's something in here that's very powerful. And so I've spent quite a lot of time looking at the stuff and playing with it since then. So the notion of a fingerprint is quite interesting. The idea is that you have something which is a complicated, a rich piece of data, a lot of bits, but you want to represent it with a small representation that is sufficient to be able to link you back to the original thing. And so it has to be there has to be enough data in the representation to distinguish between all the possible items you have to distinguish between. So it has to have some number of bits, but not a lot more than that. And so the idea is the documents exist in a very high-dimensional space, thousands or millions of bits, but there's only a certain number of them, so that if we gave them each an index, we could represent them each with 8 bits or 20 bits or something. And so the fingerprint only has to carry enough information to distinguish between those 1,000 or million different items. And so here's a very kind of sort of simple-minded example to illustrate that point. Let's say there are 4 different audio signals. Now, we're assuming that we've got some reference time base, but let's say there's something that happens and it plays one of these audio signals, but only plays one of these 4, and we know it's going to be one of those 4. If we actually had to recognize this waveform, we'd have to store a lot of information and do a cross-correlation or something like that. But instead, if we just take two samples, one at this time, one at this time, we can then get two numbers and we can plot them on some, two-dimensional plane. And then each of these different waveforms has a different value at those two times. And so we get each of these waveforms represented by a separate point here. And so then all we have to do to figure out which one of these waveforms is playing, if we know it's one of them, is take these two samples, put them on here, and then see which point is nearest. And even if there's a little bit of noise, we might get a little bit of displacement from the exact point, but we're still going to be able to make that distinction. The point is that even though the information in the waveforms is quite rich, we can still distinguish them by taking a very small subset of that information, because that's enough to tell them apart. And so this obviously is related to this idea of hash functions. A hash is something where you take a whole file, but you reduce it down to some number of bits. And the idea is that in a hash function, even if you only change one character in the file, it'll change the hash function. So that, here you could change these parts and it wouldn't even matter. But in a hash function, you have something which is a smaller dimensionality, but it depends on everything. So if you just change one part, it changes. Now, because of just because of the number of possibilities, there must be many files that have the same hash function, just because there aren't enough hash values to distinguish every possible file. But all the files that happen to have the same hash function are kind of far apart. So you're not going to change a little bit and stay the same. You have to change a lot of things to get back to the same hash function. And so that's kind of a nice property. So you don't generally get things which appear close but are different that hash the same thing. So what are the problems with fingerprinting? Well, it's these low-quality recordings. So actually, I have a whole set of actual so-called over-the-air recordings where the music's been played, and then we've recorded a bit of it just to give a realistic query. So here's an example, I think. So you can hear music playing there, but there's other stuff going on. This is the spectrogram of the recording, and this is the actual original music. And you can see that there's nothing, it's been low pass, filtered around 4 kilohertz. This is, I think it's a real recording. I think maybe the noise was added in later, but it's low bandwidth, as we're talking about, low fidelity. And there's some stuff up here, but it's not that much related to the music, or maybe it is. And there's other stuff going on. There's extra noise in the background here. And yet, does anyone know what that was? No Aerosmith fans here then. But if you were familiar with that track, you'd be able to, you'd have a hope of recognizing that. Something that a human could possibly do. So we got this channel, variation, the filtering, and background noise as a big problem. Other problems we have, obviously we don't have this nice thing of knowing exactly what the time base is. I mean, if you're just holding your phone, you're going to get an excerpt from anywhere in a track, so you have to be able to recognize a small fragment taken from anywhere in a track. And in general, if you can do it on a second's worth of audio, that'd be great. If you need to have a minute's worth of audio before you can reliably recognize it, then that's not going to be very useful in the field. If you're doing this search, you want to have the largest possible database, so you've got the best chance of actually finding the thing that's being queried for. And this is an interesting kind of problem, because it turns out if you actually run a service like this, then obviously you don't get a uniform sampling of all possible queries, that there's going to be this huge bias towards things that are currently being played on the radio or things that are currently popular pieces of music. But there is this long tail of things that people will ask you that you can't predict. And so in general, you do need a fairly large database. And then it's like, well, how large is fairly large? But it turns out that, it seems like these services are used, that a typical commercial catalog will have millions of tracks. And it seems like the services like Shazam and SoundHound are using databases of that size. And then when you're building it, essentially you've got this trade-off, which is, well, there are two things that can go wrong. You can fail to recognize something that was a real item that you did know about, but just you couldn't get enough information about it. Or you can incorrectly label something. So you can see something, think that it's something else, and report that and get it wrong. And so you have often you can trade off between these two. That, if you are more conservative, then you won't make any false recognitions, but you're more likely to reject something even if you would in fact have gotten it right if you'd allow yourself to guess it. So you have to decide how you want to balance that based on your application. So there's been these systems have been around for 10 or 15 years, and the standard approach is the standard approach for most audio processing tasks. I mean, like in speech recognition, where you have the audio and then you chop it up into short time frames, and then you calculate some features from those frames, and you represent the audio like that. So it's like the 10 millisecond frames with the 13 Kepstra coefficients or 12 chroma bins, something like that. And then so now you have this sort of sequence of vectors, and you have a query, and you do the same thing, and then you try and find the closest matching or the appropriate sequence of vectors in your reference database that matches that's similar to your query. In this paradigm, we're going to have to use features that somehow don't change despite the changes in the channel, but we can think about trying to design them that way. We're going to have issues with timing. So in particular, if we're like taking every 10 milliseconds and calculating a frame, if we have the same query, but if we have a query which is the same as a piece in the database, but we delay it by 5 milliseconds, then every frame is going to be halfway between two of the frames we had here, and so we don't want it to we don't want to make sure it doesn't differ that much. And ultimately, if we're going to do this for a million items or something, we need this matching part to be very efficient, and that turns out to be the biggest challenge in actually deploying these systems, trying to make the whole thing not need too much CPU. So one of the best described systems is the system by Heitzmer and Kalka from 2003. They actually, unusually, most of these things have been developed in commercial context, and they were in fact working at Philips. They weren't academics, but they did publish an actual full academic paper on it. So it's a nice, well-described system. And they weren't trying to deal with they were not so much worried about the recording it on your cell phone, but they just wanted to be able to record, if you have a version of the file which has maybe been put through MP3 encoding, some kind of low level of noise, they wanted still to be able to recognize it. And also some other effects like dynamic range compression. So they came up with this binary representation where you take the spectrogram, basically, of the audio, and they actually used an auditory frequency axis. So it's not a straight FFT, but it's like, some number of bands which are approximately what the ear comes up with. And then you have this local test where you take, there's one bin here, and then there are 3 nearby bins. And then you take the sum of these two diagonally placed bins, and you subtract the sum of these two anti-diagonally placed bins, and you compare them. And if this is larger than this, then you put a 1, and if this is smaller than this, you put a 0. And because these points are all nearby, on average they're going to be about the same, and so on average it could go either way. So you end up with this binary representation, which has sort of got an average of being a half, right? But locally it's got some structure. And also because it's straddling both time and frequency, if there are changes in time or changes in frequency, you're going to pick them up. And so that's what happens here. You basically have this spectrogram, but then after you've made all these comparisons, you end up with this black and white, this binary mask, binary matrix, which is now representing something about your audio. Interestingly, of course, if you scale it, then these comparisons, the ordering of these comparisons stays the same if you just change the gain. And also the comparison here is very local. So if you do something that changes one band relative to another, then that doesn't matter because you're only caring about the bands very, very locally. So that gives it a lot of the invariance or relative robustness that they're looking for. Now, there was this problem of what happens if we offset it by 5 milliseconds. So here's here's that problem illustrated. Here are a bunch of frames. Typically, we use overlapping frames, but when we calculate spectrograms, we've used like 50% overlap frames. And then if your query just happened to be, offset by 1/2 of a frame hop, then these, the closest reference item to this one is going to be sort of half that and half that, and it's going to be relatively distant from those two. The simple expedient is just to use a window which is much longer than your frame offset. So now this is the same relative frame offset, but it's now, instead of being like, 75% overlapped with some reference item, it's now 95% overlap, just because, basically we're just taking really, really small steps so that we're going to have something that fits pretty well. Another way of interpreting that is just saying that the features we're using are sort of oversampled in time, so they vary very smoothly, and so you don't, it doesn't matter how much you shift, things haven't changed that much anyway. And that's the approach they use here. So how do they do the matching? Basically, you have, an original, here's our binary mask, and so it's actually 32 bits because they use 32 frequency channels. And then they use 11 millisecond frames, but they use 256 of these things. So that would be, 90 frames a second or something like that. So they use 256 successive time frames, which is about 3 seconds worth of audio. So that's their kind of like their snapshot that they try and match on. So here's the original. Here's the corresponding chunk of 3 seconds that should match from an MP3 encode, relatively low bitrate MP3 encoding. And here's the difference, right? So here's actually all the places where these masks are not identical. And so, the white means they're matching. And there are some, significant differences here, just maybe from framing, maybe from the MP3 encoding. It seems to be more in the high frequency, and often high frequency gets dropped by MP3 encoding, so that makes sense. How are we going to find these things? So we could, for every possible reference item, calculate this difference, this XOR, as it were, and then, sum up how many bits they were different over, and if it's some small number, then, have some threshold to say, well, if it's less than 10%, then we'll consider it a match. But of course, if we've got, if we have to do that for every possible frame offset, right, because now already this is there are, we shifted by one of these 256 time frames, and we've got a whole different comparison. That could take a lot of time. So they have this nice indexing scheme, which is they look at a single frame here, which is now a single 32-bit number, and then they have all the places that exact 32-bit value occurred in the reference database. And so it's like, oh, well, that number occurred here, but you can build that as, a single inverted index. You just keep a record for all possible 2 to the 32 numbers, all 4 giga values, where they occur in your database. And then once you've got that point lined up, you then do a search over the entire mask to see if the context also matches. That would be okay as long as you were sure that exactly one of these 32-bit values was going to match exactly between the reference and the query, which, given that we've got only a few % of the bits being wrong, is quite likely here. But if that's going to make you miss some, then you could also say, well, okay, let's also try the 32 values where one of these bits is different. So I have the reference item, and then I have 32 other values where I've flipped each one of these bits, and that'll, allow me to tolerate. They only have to be within 1 bit of being identical. As long as that happens, at least in one of these 256 frames, then we'll find the match. And it turns out, this is a pretty efficient way of searching and quite feasible. So we can actually do a reasonable analysis of how these things work just by thinking about, well, if the probability of 1 bit being wrong is a certain thing, what is the probability of n bits being wrong or n bits being matching by chance? And then you come up with different schemes here, so that if you just want one of them, one word to match, you can say, well, if each bit has a 50% chance of being right, which is quite low, then the chance of all 32 of them being right is actually pretty small now, because it's only the probability of the same. Okay, probability of the same match given same audio. I'm forgetting, but yeah, I guess that this is the probability of 32-bit frame being correct. So that's fine. probability of some random frame being the same is like just assuming that it just happens to have that same 32-bit word. Even if you allow off by ones, then it's still pretty small. So it's like 10 to the minus 8, 1 in 100 million or something like that. But if you then say, well, I've got this large database of, maybe 200 million individual frames, which we got from some previous thing, you're going to find something in there that matches that, even so, just because, there's only a 32-bit variation. So a single frame isn't enough. So now you can say, well, let's have a block of them, a block of k of them. The probability of getting that match, getting 8 of these 32-bit words matching just at random is vanishingly small, right? Because it was already kind of small for just one of them, and so all 8 of them, it disappears. But also the probability of getting an exact match from the same audio becomes incredibly small too, because now we have this 0.5, which has to come up heads 8 times in a row. So the way you can get around this is by saying, well, I'm going to have some number of matches I look at, and I'm going to require that some subset of them are correct. So this is, in the Houtzma system, they're doing it at the bit level. We can do it at the word level. And so, for instance, you could have blocks of 16 words and require that 4 of them exactly match. And then the probability that you're going to get that, you're going to falsely reject something is pretty small, it's about 1%. 1% of the time, you're going to have not even get 4 of these things matching. But the probability that you'll have 4 of them matching just by chance is still incredibly small. And so you can have a plot like this, which has 2 probabilities. The probability of making a false accept, which is this red line, as a function of the number of matching words you require. And so, it falls off extremely fast. And this blue line is the probability of a false reject, the probability that even though it's a true match, you're going to say it isn't. And as the number of matching words increases, this gets pretty high. But round here, but this is a log scale, log 10, so this is like 1 in 100,000, and this is like 1 in 100. So at 4, our probability of false reject is still 1% is not bad, right? We can probably tolerate that. But our probability of false, incorrect recognition is vanishingly small. Sometimes these probabilities behave a little strangely, which is why I'm going through the math and plotting them, because it's like we still have tools that can do this. And in particular, in this case, we see that this framework, the chance of a false accept is just unbelievably small. You almost never get a false accept, but you have to be careful about how often you're going to be able to correctly accept a true match. So the other approach I want to talk about is this Shazam approach, which was developed by Avery Wang. And rather than having this sort of framework where you take individual time frames and just take whatever you get, what's clever about this is that it uses features of the audio itself to sort of define the timing structure. And so the basic idea is you take a representation of audio like this, and then you look for points where there's a sudden increase in energy. Right? You look for these things sticking out in the time frequency representation. And these become your landmarks. And then basically you're going to encode the audio by these landmarks. And then the idea is if you have the same audio, even if you shift it around in time, you're still going to get these landmarks of these same frequencies and the same relative timing. Now it turns out that the actual frequencies of the landmarks themselves, they may be quantized into 1 of 256 bins, something like that. There's not enough information there. You only get 8 bits of information to know a particular frequency is present. So you have to use combinations of these to get a bit more structure, get a bit more discriminative power out. And for the Shazam system, they take pairs of landmarks, and then the fingerprint is the frequency of the 2 landmarks, and then the time difference in between them. And so if you have 256 frequencies for each landmark, and then maybe quantize the time difference into, say, around 6 bits, 64 values, then suddenly you've got millions of distinct patterns, and now you're back into this case of like, well, none of them occurs very frequently in the database. And you can start building an inverted index that goes from these however many distinct patterns you have here to every single track where they occur. And so if you, on query, you build up your set of distinct patterns, you find all the tracks where they occur, and then you do that for all the different patterns, and then you see some tracks occurring more frequently, and that gives you your match. This is this picture is trying to show how these peaks are found. That basically you have the spectrogram, which is like an STFT, high-resolution spectrogram, but you have some kind of adaptive threshold, which is this kind of transparent level here, and then whenever the spectrogram pokes above your threshold, you move the threshold up, but you spread it out in frequency, so nearby peaks are suppressed, and then you decay it away slowly in time, so any subsequent peaks get ignored, but eventually the threshold decays enough that a peak is going to peek through again. And so this, there are a couple of parameters there, how broad and how slow it decays. But you can get a relatively small number, a relatively sparse number of these landmarks, these local peaks, being found just by adjusting those parameters. So here's the query again. And here's the match. What it's drawing here is actually the representation, right? So these little circles are the individual landmarks that were found, the ones that poked above the threshold surface. And then the lines between them are the pairs. So not all pairs. It's like, there's some range here where it looks for following peaks within a certain frequency range and a certain time range and joins them up. And so here are all this is like a 5-second query. Here are all the landmarks that were found. It's not very many, right? Which is, by design, because if we had this in our database, we'd have to store all of these landmarks, and so we don't want to store too many. This is actually the reference item, and the landmarks are stored there. And most of them are different. Most of them are not, don't match things that we pulled out of the query, but there are a few that do, right? There's sort of like 1, 2, 3, 4, 5, 6 landmarks which were the same, and then the combinations of those 6 landmarks are more than adequate to be sure this is the right match, that the chances of having these particular set of frequency peaks in some random piece of noise become very small, and so you get a good recall and precision. But one of the weird things is, of course, you could create a query that just happens to have these exact landmarks. And so this is, what I've done here is I've taken the landmarks from that query and I've just generated a little tone pulse at that particular time, which sounds like this. Right? So it sounds nothing like the original. The fingerprinter loves it, right? Here's the match. It's got all these matching points, of course, because it's the same landmarks. And so this is a false recognition, a false accept, but it's not a serious problem because you'd have to know what the original was to generate this. In fact, so that works for my implementation. I tried feeding it to Shazam. Shazam was not fooled, so obviously they're using slightly different, frequency resolutions or something. But if we knew what their intermediate representation was, we could generate one of these for that. But I've never been able to figure out exactly what it is. And so now if we do the same kind of error analysis here with some assumptions, we get a curve like this, where now the false accepts are falling down rather more slowly because it's very, very sparse information. It's just these few peaks that we're looking at. But this is the number of matching hashes that we expect out of, say, 100. And then the false rejects go up. And so somewhere in here we can get a place where we've got like 1% false reject, and we can, what I said n equals 6. So here we've got like a few per million false accepts, but we're still only a few percent false reject, which is a reasonable operating point. And of course it depends on, what noise level you want to be able to tolerate and stuff like that. One of the nice things you can do with this kind of technology is finding repeats or matching chunks within audio which are, other than just because it's being played. And so I was actually running this system on versions of Beatles tracks because I had different mastering versions of the Beatles tracks, and they'd literally been, they'd been digitized with different playbacks of the master tapes, and there was timing drift. And it was up to a fraction of a percent. It was enough that by using labels that had been manually labeled on one version of the track and applying them to the other version, I was off by seconds by the end of the track. So I was looking at the different, take one version and do a fingerprint match against the other version. So this plot is the time within the track and then the relative timing of where the matching fingerprint is. And so we see these red points down the middle as saying, yes, we're matching fingerprints against the appropriate version. And these points off the main diagonal are just chance matches where it just happens that there's some, the same little pair of frequencies at the same timing difference also occurred elsewhere in the track. But I was doing that because I was looking for like shifts or curves in this main line. And I saw these structures out here. And what that means is it turns out that here, that this little chunk of audio also matched this chunk, which was 70 seconds offset really, really well. And it turns out that it's this guitar solo in the middle of Taxman, which then is a repeat at the end. So here's in the middle. Right, so it's that solo. But that's like the middle 8 in the middle of the track. But then at the end of the track, it's the same solo, but it's during the fade out. And so it's like, is it just that they played it the same? But generally fingerprinting you could try and play it the same, it would not match because it's like these very delicate timing differences. And so I started looking around and I found this book written by the engineer who'd worked on the recording sessions at Abbey Road. And he told the story about how George Martin came in and liked this solo, which was actually played by Paul. I liked it so much that he spliced it in at the end. So it was confirmed that is a tape splice where they repeated it. This version is something similar where it's like a remix version. There's the Suzanne Vega track, and then there's a remix by DNA, I think it is. And you can sort of see where the different songs have been, different pieces of vocal have been used here to make that point. Okay, so that's it, we're done. So yeah, fingerprinting is this basic idea of trying to match the same recording despite variations in the channel, including noise. There was the idea of just using frame level matching, which works okay, but you have to be fairly, it's sort of inefficient. The thing about the Houtzner system is that you end up with a fairly large database to be able to do the matching at a reliable scale. This idea of using these local landmarks so that you sort of get rid of this problem of framing means that the Shazam system was something they could deploy. Firstly, it's much more robust to added noise because rather than looking at it, you only need a couple of frequencies to be preserved. And secondly, it scales to millions of tracks really efficiently, so they were able to deploy a big system. And we'll be playing with my implementation of the Shazam system for the practical on Wednesday. Okay, any questions? All right, great. I'll see you on Wednesday then.